Good morning. This is Dr. David Bixler, the writer for the physics questions on the Science UIL test. Although I would like to have a video that included my face being able to talk directly to you, my camera keeps crashing my computer, so I'm just going to use this whiteboard to show you what I want to tell you today. This is the third video in the series, and in this video I want to directly address the students. I want to talk to the participants, those of you that will actually be taking the science test. And what I really want to do is give you some strategies, maybe some ways to approach the physics portion that will make you feel a little bit more confident about that third section on the science test. The first thing I want to remind you of is that every question corresponds to a specific topic. The physics director notes, which are on the UIL website, lay out exactly which topics go with which questions, but I can give you a taste of it. Question 6 is always uniformly accelerated motion. Question 7, always forces and Newton's laws. Question 8, always conservation of energy and momentum. Skipping ahead, question 12 is DC circuits. Question 16 is optics. Question 18 is modern and quantum physics. So knowing the topics ahead of time allows you to pick and choose. If you're new to physics, if you don't have a lot of experience, pick a few of those questions that you're going to tackle, a few of those topics you're going to try to learn, and don't worry about the rest. Now, I know that's kind of preparation before you get to the exam, but choosing your topics and choosing wisely is a good strategy, especially for those of you that are just now starting out. Now, if you're a junior or a senior and you're in physics or you've already had physics, perhaps you're even in a second physics course, you're going to tackle most of them. You're going to try most every question. But if you're just starting out, definitely it is to your advantage to pick a few topics, go after those, and don't worry about the rest. Now, one of the topics that everyone can approach, everyone can answer, are the first 3 questions. The first 3 questions come from the directed reading. These are the book questions. This year, we happen to have 7 Brief Lessons on Physics by Carlo Rovelli as our assigned reading. But it doesn't matter what year it is. I'm always going to make the first 3 questions from the directed reading. The only strategy I'm going to give you on these, well, read the book first, but the strategy, the day before, maybe the night before, maybe even the morning of the contest, skim through the chapters that are important to that test. Again, in the director's notes, I tell you which chapters are going to be covered on the invitationals, on district, on region. Just skim through those chapters again. You might read the book over Christmas and then not take the test for a couple of months later. So it's always a good idea to skim back through. You don't have to read it in detail, but just remind yourself of the important topics, the important people, and that will help a lot when you sit down to answer those first 3 questions. Now, after that comes the astronomy question, and a lot of you already know a lot about astronomy. This is typically a very concrete-based question, a very factual knowledge type question. And how do you get that factual knowledge? Well, you read about astronomy. Read the news about astronomy. Go to NASA's website. Read some of their articles, which are written for the general public. So these are not, you don't need to know physics already to read these. Watch TV shows like Cosmos or Nova, or find YouTube channels from astronomers or astronauts discussing some interesting developments in astronomy or even just basics of astronomy. Over time, if you do this kind of regularly, you'll find that you actually gain a lot of concrete knowledge about a very interesting field. When you get to that question, you read it, there's a very good chance you'll know the answer. Now, if you have no idea, obviously, you can always skip it. Questions 5 through 18 are standard physics questions. We're going to come back to those in a minute. But questions 19 and 20 are lab-based questions. Now, lab-based questions are questions in which I give you some raw data. That data can be a graph. That data can be a table. That data may be even actually showing you some of the results that might appear during, not non-numerical results that might appear during an experiment. In most cases, these are experiments that you could do in your own classroom. How do you approach those? Well, a couple of things to keep in mind. You often don't need all of the data. If it's a table of data, you might only need one point, one XY point. If it's a graph, you might only need 1 point off that graph to be able to answer the question. If the graph is a straight line, find the slope. It's almost always, the answer is either equal to the slope or certainly related to the slope. So that's always a good idea. The other thing to keep in mind is because the data is raw data, it's not very precise in a lot of cases. So the answer choices, I often only give you one sig fig. So there's a lot of times you have to pick the choice that is closest to what you calculate. You may know exactly how to calculate things, and you'll get a number, and that number's not one of the choices. But there will be a choice that's close to that number. And we'll see that in one of the examples I'll do in a minute. So what kind of strategies do I recommend for questions 5 through 18? Those are standard physics questions. What kind of strategies are good? Well, first thing you want to do, always, draw a picture. It helps so much to visualize what's going on. Physics is inherently all around us. It's happening all the time. It's something you can see. So you should draw a picture when you're trying to solve a problem. It helps immensely. You may think, oh, I don't need to draw a picture. Dr. Bixler put a picture with the question. My picture is too small. I guarantee you, I put something in there, I had to fit it on that page. It's too small. You need to draw a big picture. Draw something that takes up an entire page. You've got tons of scratch paper. You've got lots of scratch paper. So draw a big picture that you can scribble on, that you can draw forces on, that you can write variables on. Pictures help us so much in physics. And they're critical to understanding what's going on. So that's the first thing you should always do. When you have a problem in front of you, draw the picture that represents that. Identify your known values. A lot of values are given. Like I said, most of the problems 5 through 18 are numerical. Very rarely do I make them entirely algebraic. Very rarely will you run into a conceptual question that doesn't involve a calculation. The vast majority will be numerical. So identify what values you know. Do I know the acceleration? Do I know the final position? Do I know the time it took for something to happen? Do I know the mass of the object? These are things to write down. Kind of collect them together because they're going to help you understand which formulas to use to solve the problem. When you write down your known values, pay close attention to units. Sometimes I specifically do weird units. Question 5. Question 5 is sig figs, dimensional analysis, and unit conversion. Sometimes question 5 is just a unit conversion. You're a football player, you need to gain 20 pounds in a month. Well, how many milligrams per minute is that? That's what it comes down to. So you got to convert pounds to milligrams, which means you're going from one system to another. And then you got months going to minutes, which of course is a whole lot of time conversions. That kind of a thing is question 5, maybe question 5. But even in the other questions, there will be prefixes that go with your metric units. Question 13 is about electric fields. So there's probably going to be charges involved. Charges often are written in microcoulombs, 10 to the minus 6 coulombs, or nanocoulombs, 10 to the minus 9. A lot of times in forces, you might be given a mass in grams. You need to convert that to kilograms. The system you need to be in is the MKS system. Meters, kilograms, seconds. You want everything to be in that main system. You don't want any prefixes out front except for kilo on the mass, and you don't want any English units. You want all metric. So the first thing you're going to do, write down your known values and then make sure you convert them into MKS units. Look at the question and decide what you're looking for. You know, I've seen scratch paper from contestants before who have a whole bunch of formulas they wrote down, and they tried plugging numbers into all of them. Half of those formulas didn't even have the variable they were looking for in them. They were perfectly good formulas, but if they don't have the variable in them that you're looking for, they're probably not the right one to use. So make sure you know what you're looking for. Are you looking for a final velocity? Are you looking for the time it takes for something to happen? Are you looking for the energy associated with some event? Make sure you write that down. And it doesn't hurt to write down what units it should be in. If it should be in joules or newtons or whatever, that's going to help also. You can look at the answers and see what the units are going to be most of the time. And then lastly, but probably the most difficult for many people, you need to know some formulas. Now, I don't have a formula sheet. I don't put together a formula sheet. I've been asked to, and I'm a little wary of that because there are a lot of formulas and I don't want to leave one off. I've started kind of assembling a list, but you know, there's a lot of formulas out there. Now, the vast majority of questions don't use most of those. You can narrow uniformly accelerated motion down to 3 equations. Optics, for the most part, narrows down to 2. So there's a handful of most used formulas. And you can look at old solutions to previous UIL exams, and you'll figure out which formulas show up over and over and over again. You should memorize those. You have to memorize the formula to have it when you sit down at the exam. It's probably one of the hardest parts for a lot of people, but you need those formulas right there at the tip of your tongue, ready to write down, ready to use, and you need to know how to use them. Most of the time, physics can be boiled down to a handful of formulas. Occasionally, the formulas will not work, and you have to be ready to do something different. But those are more likely going to be state, possibly regional exams. The district level, the math will not fail you, as long as you do it right. So, one other thing. I put this over here on the side just to remind myself. Guessing. I don't recommend guessing on a whole lot of questions. But if you can eliminate 2 of the choices, it becomes an advantage to guess on the other 3. There's enough points tied up in getting a question right. It's plus 6. 6 points for getting a question right. And only minus 2 if you get it wrong. So on average, if you can narrow it down to 3 choices, 3 of the 5 choices, and guess between those 3, on average you will come out with gaining points. Now that doesn't mean you're always going to guess right. nor does it mean you're always going to guess wrong. But if you can eliminate 2 of the choices, or, oh my goodness, if you could eliminate 3 of the choices, that's even better, then you can have a good shot at guessing. It's worth guessing at that point. It's a good strategy even for the biology and chemistry sections. Eliminate 2 of the choices, then guess between the other 3. I'll give you an example in physics. Maybe you don't remember the kinematic formulas. Maybe you don't know, you can't remember at all how to do uniformly accelerated motion. And the question involves somebody hitting a baseball. Baseball flies up into the stands, and you want to know the speed of the baseball. And let's say your choices are 1 meter per second, 20 meters per second, 50 meters per second, 100 meters per second, and 1,000 meters per second. You can eliminate the first and last of those. 1 meter per second? That's never making it to the stands. That's going to go a few feet and fall to the ground. 1 meter per second is really slow. The last choice, 1,000 meters per second, that's Mach 3. I don't know any baseball that could survive being hit at Mach 3. So you can eliminate the first one. You can eliminate the last one. That leaves you 3 in the middle. Maybe you don't remember the formulas. Maybe you don't know how to approach that problem. But you can guess at that point. It's worth it at that point. So there's a perfect example of when guessing might be worthwhile. Now, what I want to do at this point is go through, and we're going to back up a few pages, all the way back to page 1, and we're even going to go back to the beginning of page 1. And I'm going to take a look at a few problems, and I just want to point out the strategies as I go through. So this is a question number 6. This is a P6, which is uniformly accelerated motion. And you'll notice the first thing I'm going to do with this is I'm going to draw a picture. So I have a visual image of what's going on. Now, why does that help me? Well, it helps me see it, but it also reminds me that most of the time, most every problem, when you're talking about distances, the place where you choose 0 to be is your choice. So the initial position of this cyclist, I choose to be x equals 0. That's my choice. I can choose that to be x equals 0. So not a given in the problem, but a thing that in physics you know you can do. You can choose where x equals 0 is. And that's a powerful, powerful thing. Now, of course, I know where the other end is. The problem tells me that the final position is x equals 30. So that's given. But where x equals 0 is, you have control of that. You choose that. Here's a phrase that gives us a value. It's not written as a number, but it says starting from rest. That's a key phrase for the initial velocity equals 0. So starting from rest, pay attention when you see those words, you know the initial velocity is equal to 0. Final velocity is just given. And notice my units, meters, meters per second. We're good. We're good on the units. We don't have any worries there. No problems with that. So now I'm coming down to the equations. What equations can I use? Well, this is uniformly accelerated motion. There are 3 equations I need, or could need. There's one that relates velocity to acceleration in time, one that relates position to acceleration in time, and one that relates velocity to acceleration and position. Now, I'm going to underline in these formulas the values that we know. Initial velocity, initial and final positions. And now let's circle what we don't know. I don't know time. I don't know acceleration. I'm looking for acceleration. It's in all three formulas, so I can't really go wrong. But if I have two unknowns, that's not good. I'm not going to be able to solve that. This one has two unknowns also. I might be able to combine those equations and solve, but basically you really don't like that. If you can have one unknown, it's better. And look what happens down here. There's only one thing that I don't know down there. So that's the equation I want to choose. I've got three possible kinematic equations, but two of them are less than perfect. I've got one equation that will allow me to solve this problem right away. So let's take that one. It's the v squared equation, I call it. Plug in our values, solve for acceleration. We happen to notice that's choice D. It is often true that if you have a series of formulas, one of them will be the best choice. In uniformly accelerated motion, the v squared equation is used a lot. So if you don't know which one to use, try it first, because you never know. Very rarely will you have to combine formulas or do any algebra to solve. If you've got all the formulas in front of you, chances are one of them will work well. And that's the case here. So for the second problem, I want to take a look at an optics problem. Now, optics is P16. And in this case, I've got a couple of lenses. I've got a couple of distances given. The whole thing is set up in centimeters. Notice the answer is also in centimeters. Optics is one of the rare places where if you are given numbers in centimeters and answers in centimeters, you actually don't have to convert to meters. You can stay in centimeters the whole time. It doesn't happen in very many topics, but it does happen in optics. So we're going to do that here. Of course, first thing I'm going to do is draw a picture. I know the picture's right there, but I need something I can scribble on. There's only two formulas in optics, really. The first one, 1 over P plus 1 over Q equals 1 over F, that is for finding where the image is located. So you have an object, you have a lens, there's going to be an image somewhere. That tells you where. Q is the image location. And then the magnification formula, which we don't even need for this, because notice what we're looking for is where is the final image located. We're only going to need that first formula. So that's actually a good thing. When you're faced with two lenses, you actually just work with one lens at a time. Kind of ignore the second lens. So I've got my values down there. I've labeled them. They were actually already largely labeled. P1 is the object location for lens 1. F1 is the focal length for lens 1. We could just plug that into a formula, the formula for finding the image. I mentioned we can stay in centimeters. And what we find here is the image location formed by lens 1. So my picture, I'm going to draw it. Interesting thing to note, it's past lens 2. That doesn't matter. It's fine. Math still works. But something interesting is about to happen. And what's about to happen is we're about to shift over to lens 2. Shifting over to lens 2 means translating your axes. We basically move over 14 centimeters, but it's not as straightforward as it might seem. We actually have to subtract Q1 from D, from 14 centimeters, to get P2. P2 is the object distance for lens 2. Notice when you subtract these, you get a negative number. So I have a negative object location. What does that mean? What kind of craziness is that? It just means your object is to the right of the lens, which we can tell from the picture. It doesn't matter. It doesn't cause any problems. You need to keep the negative sign with it, but it doesn't cause any problems. A negative object distance is perfectly okay. It just means it's to the right of the lens. The right side of a lens is a negative object positive image area. So it's perfectly fine. So I'm going to draw my second lens. I switched pages, so I had to redraw my picture. I know where my object for this second lens is located. Going to go back to that same formula, plug in the -14 and the focal length, which is -19. And I get a positive image location. Positive image is on the right also. So the right side is going to be a positive image, but a negative object. So that means it's over here. Past, of course, where our object was. Pretty far out, actually. If you look at your answer choices, you'll see that that happens to be E, 53.2 centimeters, to the right of the second lens. So that's a good piece of information there. Not always will you be faced with two lenses, but obviously if you could do two lenses, you can do a single lens along the way. Only a couple of formulas to memorize. Not bad. Let's go to an electric field question. Now this one's a different type of question, and you can kind of tell because just look at the sheer number of values I give you, known values. There's a lot of them in here. We got a mass in grams, need to convert that to kilograms. We got a charge in microcoulombs, which we need to convert to coulombs. We've got a distance in centimeters, and for electric fields, you need to convert that to meters. We've got a voltage in volts, which is good. We don't have to change anything. No conversions there. And then I have another distance, a delta x, in centimeters. I need to convert to meters. This many numbers is a huge number of things. What am I looking for even? Oh, I'm looking for a speed, a final velocity. Oh, and along the way, the dust, it's a particle of dust, it starts from rest. So I know an initial velocity is 0. So many pieces. Means you're going to have to draw on a lot of formulas. Many equations have to be pulled together. 4 of them to be exact, but they're not all from the same topic. And this is the place where the more formulas you can have at your disposal, the better you will perform on this part of the test. For example, these two come from the topic of electric fields and forces. But that's Newton's acceleration law, Newton's second law. So that's from back in question 7's topic. And that's a kinematic formula from question 6's topic. You can kind of figure out which formulas you need based on the variables up here. Look, Q and V and D, the voltage, the charge, the distance between the plates, that goes with the electric fields and forces. But mass, as soon as mass gets thrown in there, you're probably using Newton's second law. And when you have velocities and distances, that's kinematics. You're almost always going to end up with kinematics. Or energy, but easy enough to approach it from this perspective. So lots of things to pull together. Now, once you do pull them all together, solving the problem is really easy. It's a plug and chug, as we call it. You plug in, find the electric field. That's the first formula. Use the second formula, find the force on this particle of dust. Use the third formula, find the acceleration. You do have to rearrange F equals ma because you need to solve for A. Then use your kinematic formula to solve for the final velocity. It is about as straightforward of a solution as you can get to, but there are a lot of formulas there. Well, 4 of them, but they come from a variety of different branches of physics, and that's what makes it perhaps a little more challenging. By the way, the answer choice C is the correct one. Now I want to take you to a P9. P9's rotational motion. It doesn't mean things have to rotate. Statics problems end up under P9. So this is an example of a statics problem. If any of you ever want to be engineers, you take an entire course on statics. So this is a really important topic. This one, in this example, I have a flagpole. It's attached to a building by a bolt. There's a cable helping to hold it up. You really need a free body diagram, though, to work these problems. So that's what I'm going to start drawing. Take the picture, draw it. Now let's draw some forces on it. The first force, weight. The weight of the flagpole itself. Now, where do you draw that? You draw it at the center of mass, which, for a uniform flagpole, is right in the middle. Right there in the center of it. We have a tension. Oh me, oh my. This tension's at an angle. So we're going to have to deal with that. And then the bolt itself has both horizontal and vertical forces acting on it. So we have a horizontal force, FH, and a vertical force, FV. What we're looking for is actually the vertical force. We're looking for that FV. So that's what we're going to need to solve. Let's deal with that tension. One of the most important things that you can remember from your math courses, specifically from geometry, is your right triangle geometry. Sines and cosines in particular. So here we have tension, but that's at an angle. I need the horizontal component of tension, and I need the vertical component of tension. I have an angle of 40 degrees, so we can see that the cosine of 40 degrees will give me the horizontal, the sine of 40 degrees will give me the vertical. So that's how we break that up. We're not going to ever worry about t by itself. We're going to worry about its horizontal and vertical components. By the way, weight equal to mg. I think you probably know that, but it's always something important to keep in mind. We know the mass, by the way. It's 3.5 kilograms. It's already in kilograms, which is nice. We have some distances. I'm going to choose 0 to be at the wall, where the bolt is. You can choose 0 to be anywhere, remember? You always get to choose 0 to be anywhere you like. I'm going to choose it to be over there. The flagpole's 1.3 meters long, so that means the end. And the weight, I said, was at the middle, is halfway. So that's going to be halfway along, 0.65 meters. Now, to solve a statics problem, you basically add up forces in the horizontal, set them equal to 0. Add up forces in the vertical, set them equal to 0. And then add up torques and set them equal to 0. Nothing moves, so everything equals 0. So the horizontal forces. Now, we take to the right to be positive and to the left to be negative, or subtracted, I guess. So we've got a horizontal force at the bolt that's pointed to the right, and then a component of tension to the left, so that's why we subtract that component of tension. Set that equal to 0. For the vertical, up is positive, down is subtracted. So we're going to set all of that equal to 0 also. We've got the bolt force going up. We have a component of tension also going up. And then we have the weight, which is going down, which is why it's subtracted from the others. And then there's the torques. Torques are tricky. They're basically a force times a distance, but there's some rules about that. And the first rule is that only the forces perpendicular to the object, in this case the flagpole, only those perpendicular forces cause a torque. Forces that are horizontal, in this case, are not going to cause any kind of a torque. So we only have to consider the vertical forces. Fortunately, we have them listed right above us, so that makes it a little bit easier. Torque is force times distance, so we take those forces, in this case, the vertical bolt force, the weight, and the vertical component of tension, and we multiply them by an appropriate distance, like how far are they from x equals 0. So That first one's actually at x equals 0, so it's going to just vanish anyway. Now we got to decide which ones are plus and which ones are minus. Which ones do we add? Which ones do we subtract? Well, the rule is if the force wants to cause a clockwise rotation, then it's negative. If the force wants to cause a counterclockwise rotation, then it's positive. Well, that vertical force of the bolt is at position 0, so it's really not going to cause any rotation. But the weight, if you think about the weight pulling that flagpole down, that's clockwise. And the tension is pulling it up, that's counterclockwise. So the weight needs to be subtracted, the tension needs to be added. And this all equals 0. Now, we can get rid of that first term because it is at x equals 0, so we don't even need to concern ourselves with it. And then we can plug in mg for the weight, 0.65 for the distance over to the weight, and 1.3 for the distance over to the tension. We have all of those numbers except the tension itself. The torque equation almost always is the most important equation. It's the first one that's going to give you one of your unknowns. In this case, it allows us to calculate the tension in that cable. So the torque equation is really important. And I know it's the hardest one to write down. And some of you have already given up on this problem, but when you learn how to deal with torques and rotation, you will see that that torque equation is always kind of the key equation. It allowed us here to solve for tension, which I can plug back in to the vertical force equation. And from there, I can solve for the vertical component of the bolt force. There we go. That's choice A, by the way. Notice the horizontal force equation I never even used. That's okay. The equation was right. I just didn't need it. And that's okay. Doesn't cause any harm. So lastly here, I wanted to take a look at one of the lab-based questions. I mentioned earlier I'd take a look at one. And in this case, this is a diffraction problem. You place a human hair in a laser beam, and it creates a diffraction pattern on the wall. Now, you're not given a table of data, you're not given a graph, you're actually given a picture of the diffraction data. So you're going to have to read your own values off that scale. Notice the answers have 1 sig fig. That's what happens when we do these lab problems. We don't have necessarily a lot of precision in them. This is raw data. So we're going to be working with very approximate kinds of numbers. What do we have and what are we looking for? Well, we have the data. We have a wavelength. We have a distance to the wall from the hair. And we're looking for the diameter of the hair. So first I need to figure out what this data is telling me. Diffraction patterns, the important fringes are actually the dark fringes. So I'm going to estimate where the dark fringes are. I get to choose where 0 is again, but you would always choose that to be the central spot. It's just the nature of diffraction. After we do that, I can estimate, say, the first couple of dark fringes. I'm going to have to average those, well, find an average value of the distance to a dark fringe in a minute. I'm going to write down my wavelength. I need to convert that to meters because it's in nanometers. So we've got 10 to the minus 9 in there. And the distance to the wall is called capital L. That's going to be important for calculating some of the geometric quantities we need. My average here is about 1.35. Now the reason for that is I have 1.3 for the first fringe, 2.8 for the second fringe. Well, the second fringe should be twice as far out. So basically I take the 2.8, divide it by 2, that gives me a 1.4. I average the 1.3 and the 1.4. Gives me 1.35 centimeters. I do need to convert that to meters. Now the formulas for diffraction, basically this is the most important one. A sine theta equals m lambda. A is the diameter of the wire or hair in this case. So A is what I'm looking for. Sine theta is it was based on the geometry of the setup with the laser and the hair and the wall. M, well, M is an integer. But the way we work these problems, the way we always work these problems, is M is 1. Because what we really are looking at is what's the average distance between adjacent dark fringes. Well, the average distance between adjacent dark fringes is going to be an integer of 1, because it goes from, say, the 7th dark fringe to the 8th dark fringe. Well, that's a distance of 1 fringe. So M is going to basically always be 1. Or in our case, I guess we're actually going from the 0th to the 1st, but it's still a distance of 1. So M, usually 1. If you're guessing and you don't really know, just pick M equals 1. It's probably going to be right. To get that angle, I'm going to have to use the setup that I have, which means we need that value for L. How far are we away from the wall? And we have to use tangent in this case. Tangent of theta is equal to x over L. Now, when you're working with diffraction and interference, the angles tend to be actually pretty small. So I'm going to go ahead and calculate this. I put x over L, inverse tangent that, take the inverse tangent, and I get 0.52 degrees. So as I mentioned, angles tend to be very small in diffraction, single slit diffraction, and interference problems. You usually have small angles. A diffraction grating, if it says the word grating, that's going to be a bigger angle. But if it doesn't use the word grating, we're probably going to deal with small angles. Some of you may have been taught the small angle approximation, and you would be perfectly fine in using it here. But I'm not using it in this case because I wanted to write everything out properly. Once you have the angle, I can plug in the m equals 1, the integer, plug in the wavelength, plug in the angle, and solve for A. So that's the answer I want. That is the diameter of the hair. Now I need to convert that to micrometers, because that's what the answers are given in. And notice I get 64. Now 64 is not one of the answer choices, but it is closest to 60 micrometers. There's a 40, there's a 60, there's an 80. The closest one to the number I calculated is the 60, and that is the right answer. Depending on how you read that scale, you might get 58 or 61 or 62, but you're always, always, always going to be closest to the correct answer. And so the lab questions, one of the strategies is to remember that you're not going to get the exact right number, but you are going to get a number that is closest to the right answer. So that's something to pay attention to on those. So that's the last example I was going to show you, and I hope that this is useful for helping you develop some good habits. If nothing else, draw a picture, watch your units, and make sure you know at least some of your formulas. All right. I wish you all the best of luck, and hopefully I hope to see some of you in person this next spring.